Recall that to figure out where a two-dimensional ray intersects a line segment, we started by first introducing a coordinate system. Once we have our coordinate system, we can write our line AB in slope-intercept form. Since in this example, A has coordinates 3, 2, and B has coordinates 4, -1, the slope-intercept form of AB is y equals -3x plus 11. Similarly, if I pick P to have coordinates 2, 1/2, then the slope-intercept form of the ray CP is y equals 1/4 x. The point I we're looking for is on both of these lines. So if I sub x and I sub y represent the coordinates of I, then I sub y equals -3 I sub x plus 11 because I lies on AB. And I sub y equals 1/4 I sub x because I lies on the ray CP. Solving these two equations for the two unknowns gives us the coordinates I sub x and I sub y. Using the slope-intercept form of the ray works in 2 dimensions and is fairly simple to understand, but there's a problem when we generalize it to 3 dimensions. The problem is that in 3 dimensions, the ray doesn't have a slope-intercept form. So we'll have to throw out this representation of our ray in preparation for 3-dimensional ray tracing. To represent our ray CP, we'll use something called a parametric function. What I'm about to write looks a little strange at first, but bear with me. These functions start to become familiar with practice. My ray will be represented by a new function, r of t, that is a weighted average of C and P, where T is the weight. In particular, I'm going to write r of t as 1 minus t times C plus t times P. Notice what happens when t equals 0. 1 minus t is just 1, so r of 0 is C. And when t equals 1, r of 1 equals P. That's convenient because I can relabel C as r of 0, and I can relabel P as r of 1. R of 1/2 would be exactly halfway between C and P. Values of t greater than 1 name points on the ray off in the scene beyond P. Before we continue, get some experience using this kind of parametric function in the next exercise.